Another type of electrolysis that we can look at, and the book goes into pretty decent detail about this, is the electrolysis of water. And when we're trying to solve the energy crisis that we're faced with, we have looked into the hydrogen fuel economy. And in this particular case, if we can get hydrogen from water, it would be great. Because we would then have an abundant supply of water. We could then have an abundant supply of hydrogen. So the question is that feasible to use electrolysis for this breaking down of water into hydrogen and oxygen? So typically the way this process works is we can take a beaker of water, and if we set it up with the anode on the left and the cathode over here on the right, and we put a platinum wire and a copper wire in this water solution, and we connect them through a wire and pass a current. These two double lines here means we're passing a current through here. If we typically draw a circle with a V on it, that means we're just measuring that potential across. So here we're applying a current, and we have a solution, or an aqueous solution of water down here. Typically, to help facilitate the process, we'll put some kind of ions in there. H2SO4 is sometimes used. Na2SO4 is also used. But in this main process, if we set this process up like I have drawn, it's going to start to bubble gases, and gases are going to start to form. We can collect the hydrogen and the oxygen gas. So if we look at the specific reactions that occur at the anode oxidation occurs. So we have two waters as a pure liquid being oxidized into O2 gas plus 4H plus 4 electrons. This potential is equal to negative 1.23 volts. The cathode half reaction, or the reduction half reaction, is going to be 4 waters being reduced to 2 hydrogen molecules plus 4 hydroxides. In this process, we need 4 electrons over here on the reactant side. The cell potential for this half reaction is negative 0.83 volts. In terms of the overall reaction, the 4 electrons cancel out. And over here on the left-hand side, we have 6 waters giving us 2 hydrogen gas plus oxygen gas plus 4H plus in aqueous solution plus 4 OH minus in aqueous solution. If we have H plus and OH minus present in the same amounts in aqueous solution, they're going to neutralize each other. And these guys are going to form 4 waters. So these 4 waters will cancel out with 4 of these, leaving 2. So our overall net reaction for the electrolysis of water is going to be 2 waters as a pure liquid, giving 2 H2 gas plus O2 gas. The overall standard cell potential for this particular reaction is negative 2.06 volts. And if you're trying to produce hydrogen from water, you're going to say, yikes. Freaking negative 2 volts, that's a lot of energy to overcome. And it just so happens that in order to produce enough hydrogen to be efficient, it takes more energy than we would get out with hydrogen as a fuel. So this is not an effective process because this voltage is so high, and more importantly, it's so negative. Because remember, a negative cell potential indicates a non-spontaneous reaction. So we can kind of do some calculations based on this as well. So if we have this particular reaction right here that's balanced out, we can ask the question, what volume of hydrogen gas can be liberated during the passage of 2 amps for 30 minutes. So if we have 2 amps, we have 2 coulombs per second. 30 minutes can be converted to seconds by multiplying by 60. We also know that 96,486 coulombs is equal to 1 mole of electrons. In this particular passage, we have to go and look up at the half reaction involving hydrogen. If we look up at that reaction, for every 4 electrons, or 4 moles of electrons, we have 2 moles of H2. If we're under standard conditions and we're trying to figure out a volume of hydrogen that we're going to collect, we know that if we have 1 mole of hydrogen gas, under STP we have 22.4 liters. So if we're under standard conditions, for every 1 mole of that gas, it's going to occupy a volume of 22.4 liters. If we multiplied all this out, that's going to give us 0.420 liters of H2. So if we're given a particular current, in this case we have 2 amps, we can use that value, and Faraday's constant comes in and plays a huge role in all of these calculations, because that's going to allow us to relate the number of coulombs that we have to the number of moles of electrons. So when you're setting these up, you're definitely going to have to use that Faraday constant, and you need to make sure that you know how to manipulate these guys. So if you're asked for a volume of a gas, you also have to remember that at STP, 1 mole of a gas is going to occupy a volume of 22.4 liters.